Hello, and welcome to this short course on models of social dynamics. I'm Paul Smaldino. I'm an assistant professor of cognitive and information sciences at the University of California, Merced. In this unit, we'll tackle cyclical social behaviors. We've modeled a number of dynamical systems in this course, dynamical social systems. However, one thing pretty much all the systems we've looked at have had in common is the tendency to evolve toward a stable equilibrium. Yet, social life is pretty much never at equilibrium, despite what your friendly neighborhood economists might tell you. Instead, much of life is cyclical, right? So, a time of war, a time of peace, a time to dance, a time to mourn, a time to cast away stones, a time to gather stones together. As this passage from the book of Ecclesiastes, or the birds, depending on your source, indicates. Right? So in the last modeling unit, in this last modeling unit, I should say, we're going to explore a couple of models that allow for cyclical behavior. So what's needed for cyclical behavior often is feedback and delay. That is, the dynamics that give rise to growth must not only contribute to eventual decline, but have to do so with enough of a lag that growth doesn't simply reach a stable equilibrium, but exceeds the conditions for stability, overshoots it, and therefore has to decline, with the decline also overshooting the equilibrium point. And that's one of the ways you get cycles. A number of mechanisms can give rise to cycles. One of the most well-known, and one that we've encountered already in this course, is the Lotka-Volterra predator-prey dynamics that were developed in the 1920s. Right? The purpose of this model, which I discussed in Unit 1, was to explain the widely observed phenomenon among hunters and fur traders that populations of predator and prey species tended to repeatedly rise and fall on similar timescales. So, for example, Hudson's Bay Company in Canada noticed cyclical patterns in the populations of the animals they hunted, like the Canada lynx and the snowshoe hare. Not only did the populations both rise and fall, but their cycles seemed to be locked in phase and unexplained by external factors like climate. So the model is analyzed using coupled differential equations, but its assumptions are very simple. In the absence of lynx, hare will reproduce and increase in number. In the absence of hare, lynx will starve and decrease in number. When both are present, lynx will eat hare and increasing their numbers while diminishing the hare, their food source. So here we're going to begin by exploring a related model, the ecological host-pathogen model. This is a very simple model, but it can lead to complex and sometimes counterintuitive outcomes. After exploring that simple model, we're going to explore one that's considerably more complicated, but operates on similar principles, looking at the rise and fall of empires. So let's start with the ecological host-pathogen model. In this model, there is a host species that can become infected by a lethal pathogen. Spatial locations on a grid can represent either susceptible hosts, infected hosts, or empty locations on which hosts can reproduce. Pathogens infect hosts. The pathogen spreads by passing from one host to another, and an infected host will eventually die from illness. If there are no nearby hosts, the pathogen cannot spread. And hosts can reproduce when they're healthy, but not when they're infected. And in this model, one of the things that's interesting is we're going to use the patches themselves in NetLogo as the agents. We're not even going to use turtles. The model assumptions lend themselves to other possible interpretations beyond hosts and pathogens. So for one, the model is similar, as I discussed, to the Lotka-Volterra predator-prey model. And you can embrace this similarity more directly. So you could say the hosts correspond to prey and the pathogens to predators. In this interpretation, prey reproduce in the absence of predators, but are killed by predators, while predators reproduce after killing prey as long as another prey population exists nearby, but they die in the absence of prey. Another interpretation, yet, is possible in terms of human populations. You could say these are consumers and resources. Consumers use up renewable resources to reproduce, which depletes the resources. In the absence of resources, consumers perish, but resources renew in the absence of consumers. For simplicity, though, I'll continue to talk about this model in terms of hosts and pathogens. So this is actually one of the simplest models to code. It's so simple that you might ask why I didn't start the course with this model. It's quite a bit simpler in terms of its coding than the contagion model that we looked at in Unit 2. One answer is that it allows me to point out that a more complicated model isn't always better or more sophisticated. You're not necessarily a better modeler if your models are more complex. Rather, you should strive for the simplest possible model to capture something interesting about your system. Another reason is that although the model assumptions are simple, its dynamics can appear quite complex. And a final reason is that the final model we're going to consider in this unit is actually very complicated, and the host pathogen model provides a useful bridge to it. Okay, so like I said, for this model, we're going to use a square grid, as we've been doing, with agents paying attention to their nearest 4 neighbors, up, down, left, right. The cells of the grid are going to be the agents, and they can take on one of 3 states: empty, susceptible, and infected. The model is pretty much fully defined by the grid structure itself and the rules governing the transitions from one state to another. So let's take a closer look at how those transitions are formalized. So first, empty cells can become hosts. An empty cell becomes a susceptible host if at least one of its neighbors is 1, and so reproduces onto it. A susceptible host attempts to reproduce onto a neighboring empty cell with probability R, the reproductive rate. We say attempt because at maximum only one neighbor can be successful. In our model, all hosts are identical, so the probability of going from an empty cell to a susceptible host increases in a very straightforward manner with the number of neighbors that are susceptible. So let's let the probability of transitioning, let's let n sub s be the number of s neighbors, susceptible neighbors. The probability of transitioning is equal to 1 minus the joint probability that none of the 1 susceptible neighbors attempt to reproduce. So in this case, it's just this, right? Just like we saw before in the contagion model. Next, susceptible hosts can become infected hosts. A susceptible host becomes infected by one of its infected neighbors with probability tau. This is sometimes called the transmissibility of the pathogen. As before, the probability of becoming infected increases with the number of infected neighbors, and again is equal to 1 minus the joint probability that none of one's infected neighbors transmits the pathogen. So n sub I is the number of infected neighbors. The probability of transitioning from a susceptible host to an infected host is just this. Again, just like n sub s, n sub I can be a number, is always going to be a number between 0 and 4. Okay. Finally, infected hosts can become empty cells. Infected hosts die with a probability equal to V, the virulence of the pathogen. This transition probability does not depend on the state of one's neighbors, only on being infected. Right, so unlike before, which the things that involve reproduction, the more neighbors you have, the more likely it is that one of them is going to reproduce onto you. But an infected cell just dies with a probability that is the virulence of that pathogen, and it doesn't matter what the state of the neighbors are. Okay, so the model has 3 parameters that govern how the cells transition from one state to another. In our version of the model, empty cells will be black, susceptible hosts will be green, and infected hosts will be red. We'll initialize our model with a healthy population of susceptible hosts and an infection breaking out among just one of them. See what happens then. So let's open our spatial host pathogen model looking at Host-Pathogen.nlogo. Check it out. All right, here we go. So as you can see, we've got 3 sliders representing the 3 model parameters: the reproductive rate, the transmissibility, and the virulence of the pathogen. So let's see what happens. Set it up. All right, let's look at the code first. That's it. That's the entirety of the code. It's really simple. First, to set up the model, we set all the patches to green, and then we make the center patch red. Done. Okay. The dynamics. Ask patches. Each patch checks its color. If it's black, so if it's empty, it becomes a susceptible host with a probability dependent on the number of neighbors that are susceptible hosts, just like using the equation we just discussed. If it's green, if it is a susceptible host, it becomes infected, depending on the number of neighbors it has that are infected with the probability we just talked about. And the same thing, if the cell is an infected host, it dies, it becomes an empty cell with a probability equal to the virulence. And that's it. Kick, and it does it over and over again. Very simple model. Let's see what happens. So I will note that the models in general in this class are running a little slowly because I am recording my screen. And my MacBook Air isn't quite up to the task of both recording and running the model at full speed. I do promise that these models run quite a bit faster when I'm not recording. Okay, but look what's happening, right? The population of the infected cells is going up, and it's going down, and it's going up, and it's going down. The pathogen spreads from host to host. The virulent pathogen kills its host quickly, and it limits the number of new hosts available to infect, and then fizzles out. So this allows susceptible hosts to recover and provides new fertile soil for the spread of the infection. So this manifests as cycles of widespread infection and recovery. If we explore the model parameters, we can get some interesting, and I think a little bit counterintuitive results. So, for example, you might think that if we increase the rate of reproduction for susceptible hosts, this is going to provide for a robust population and diminish rates of infection. Right? The susceptible, pathogen-free hosts can reproduce faster. So let's see what happens. I increase the reproductive rate from 0.1 to 0.1. And look what happens. Right? The opposite happens. Higher reproductive rates for hosts actually favor the pathogen. This is because there are now more susceptible hosts to which the pathogen can spread, and there's no empty regions persisting long enough to block pathogens from spreading before they kill their hosts. So, sort of spatially, it shifts from what looks to me like an army of pathogens moving methodically over the landscape, and now it looks kind of like a fierce boil of life and death. And you can see on this graph here, the cycles are a lot quicker, and the average population of infected hosts goes up and uninfected hosts goes down. So the rate of infection has increased with higher host reproduction. But what we probably want is a less virulent pathogen, so fewer hosts are killed, right? Let's see what happens. Let's decrease our virulence from 0.1 to 0.04, so we're going to be a lot more virulent. Oh no! Again, the opposite happens, right? When we lower the virulence, the infected hosts now outnumber the uninfected hosts, and the number of empty cells has boomed. There's just way more hosts. Instead of the infection spreading through a healthy population, it looks almost like the susceptible hosts are fleeing the rampaging infection. This happens because the infected hosts don't die off as quickly, but they stick around to infect more of their neighbors, and this actually enhances the spread of the pathogen. So here, right, if I keep decreasing the virulence, so now it's a less virulent host. The population just basically collapses. If I let this run long enough, I think it will probably collapse. All right, in this case, it hasn't collapsed yet. And it's a fun model to play around with. Check it out. All right. So, to summarize, the inhibitory/excitatory dynamics of spatial arrangement give rise to oscillations in this model. We saw that increased reproductive rate actually leads to decreased host populations, and decreased virulence actually led to an increased chance that the host population is wiped out, and certainly to more infections and a less healthy population overall. So I really encourage you to play around with this model. It's pretty fun to watch. So I think this is a really cool model, but it might not be totally clear how this model applies to the sorts of things that social scientists who are not epidemiologists are interested in. I think it's interesting, but your mileage may vary. So, as our final model in this course, we're going to do one more. Let's consider something a bit more ambitious: the rise and fall of empires. Much of the history of civilization, the last 5,000 to 10,000 years of human history or so, can be viewed in terms of the rise and fall of empires. The general story that is often told about human history is one of continued growth. After the agricultural revolution, about 11,000 years ago, humans in many parts of the world became more tied to location and saw rapid increases in their population size. This newly increased population facilitated division of labor, organizational challenges that were in turn well solved by larger and more hierarchical governance structures. That's often the story that gets told, but people don't so readily give up their group identities and join with other groups. Just because a population grows doesn't necessarily mean groups will join together. However, with growth also comes a new type of scarcity, and that breeds competition. And the result is often war, which is widely thought to be a major driver of societal complexity. Though the strong version of this claim can be summarized by the sociologist and historian Charles Tilly, famously said, "War made the state, and the state made war." With war comes conquest, and therefore we see not only the rise but also the dissolution of empires. You can see this by looking at this data, which shows the size of empires in East and Central Asia over a 600-year period as empires rise and fall and collapse and come into being, etc. So why exactly does this happen? Why would competition give rise to cycles of empires rather than more stable equilibria? I think we need to turn our ideas into models. So history is complicated. History definitely seems far messier than most, if not all, the systems we've tackled so far. The short answer is that it's very difficult to model this sort of thing. But difficult is not the same as impossible. If historical dynamics are subject to patterns and forces that recur with at least a modicum of regularity, then those dynamics are modelable. And as always, we can start with a model that is drastically simple, but nevertheless captures some of our key assumptions about how our system might work. And I'm going to tackle one particular theory of history of the rise and fall of empires, what is called metaethnic frontier theory. So this comes from the ecologist turned historian Peter Turchin in his 2003 book, Historical Dynamics. He attempts to explain some of these historical cycles using what he calls the metaethnic frontier model, which developed the idea that empires foster a superordinate or metaethnic identity among their citizens. The theory is actually an extension of one developed by the 14th century Arab scholar Ibn Khaldun. So, a key concept in the model is Asabia, an Arab, which I don't know if I'm pronouncing that correctly. Asabia, should have looked it up. I didn't. Moving on. This is an Arabic word denoting a sort of social solidarity with an emphasis on unity, group consciousness, and a sense of shared purpose. Note that asabia is a property of a population, not an individual. So it's a group level trait, something that I've written about. Group level traits are inherently challenging to model as emergent phenomena. So, like many other models, we're just going to take the trait as given. The theory proposes that polities that share borders with different polities will be bolstered in their sense of asabia, which will be important for producing group-level phenomena like warfare and empire building. As empires expand their territories, their increased access to resources are going to drive further growth. However, as empires become larger, asabia among those individuals who live far from the frontier will decline as a result of increased internal competition and a lack of resources, lack of exposure to external threats. Meanwhile, the constraints of expanded infrastructure mean that maintaining a frontier becomes more difficult as the empire's size expands. So eventually, an empire can be stretched too thin and it becomes susceptible to conquest. And that's basically the idea. Empires that are polities that are neighboring to other polities, because of the inherent differences, increase a sense of shared solidarity that allows them to cooperate and actually go to war and conquer other groups. Conquering other groups, right, increases their ability to continue to do so when they grow and grow, but expanding also creates its own problems, which eventually degrade the empire's ability to maintain itself, and it allows it to become susceptible to conquest by another group. So the theory says nothing about how the first empires form, and it doesn't account for many other factors like geography, topography, and technology. Nevertheless, it's grounded in reasonably well-founded notions of human society, and it's clear enough to be formalized. Formalization will help us see how precise and plausible the theory might be. So, let's translate this theory into a model. So the model works as follows. Right? The smallest spatial unit in the model, which is going to be a cell on a square grid, corresponds to a small regional polity or chiefdom. So these are the black zeros in this figure. Each one is a different chiefdom. However, the polities can become absorbed into a large territorial empire, and so the cells all have an imperial index denoting the empire to which they belong. So the chiefdoms are all have an index of 0, but they're all separate. And then here I've depicted another empire with an imperial index of 1. That's the red cells, and they're all one empire. So the idea is each cell has a level of asabia, S, and this represents the average degree of collective solidarity felt by its population, and it's determined by the position of the cell relative to its imperial boundaries. So asabia grows logistically to an upper limit of 1 if it's situated next to a boundary between two empires or between an empire and a chiefdom. If the cell is not on a frontier, asabia declines exponentially to 0. The idea is basically if you're far from a frontier, internal conflict and the lack of external conflicts lead to a degradation of solidarity. So in determination of its frontier status in our formalization, the cell is going to consider yet again only its 4 nearest spatial neighbors. Territorial empires are characterized by 2 numbers. One is the number of regions they control, their area, A, and then the other is the average asabia of those cells, S bar. And I don't know if you can hear the soothing sounds of my cat yelling in the background, but we'll continue. Okay. At each time step, every cell is going to consider an attack on its neighbors, each of its 4 neighbors. So cells that are part of the same empire never attack each other. So a cell never attacks another cell that's part of the same empire. But otherwise, any other thing is game, is up for grabs. A successful attack occurs if the power of the attacking cell is sufficiently greater than the power of the defending cell. If it's if the difference in power is above a threshold. Oh, that says an empire collapse, so that should be about a threshold. Anyway, okay. Power of a cell is dependent on three factors. One, power increases with the asabiya throughout the empire. So this indicates the importance of social solidarity and military victory. Power increases also with the total size of the empire. This indicates that more resources available to the military increase power. But power decreases with the region's distance from the imperial center. This indicates the time and energy needed for communications and resources to travel. So formally, the power of the cell is given by this equation. It increases multiplicatively with area and asabiya and decreases exponentially with distance from the imperial center. So d sub ij is the distance from the cell to the imperial center, and h is a parameter determining how rapidly power declines with increasing distance from the imperial center. If the distance, the difference between the attacker and the defender cells is greater than some delta p, the defending cell is taken over and its imperial index is made to join the empire, the existing empire. Finally, an empire can collapse completely if its average asabiya becomes too low. So if its average asabiya is below some critical threshold, S sub crit, the empire is dissolved and all its cells become independent chieftains. Okay, let's check out the model. The primary question for this model is going to be, do we observe cycles of the rise and fall of empires that look anything like those seen historically? This model involves considerably more coding than previous models. So as with the previous models, I've provided the code. This one may take a little bit more work to understand than the others. So in general, some computational models are quite complicated, and some of them are considerably more complicated than this one. It's important to consider how many assumptions are necessary, and to always make the model as complicated as necessary, but not more so. Due to the complexity of this model, I'm not going to go through most of the parameters, but rather I'll leave it as an exercise for the curious student. In general, I'm going to use the parameter values that are used by Peter Tertian in his book, unless noted otherwise. All right, so we can open up metaethnic.nlogo. And notice here, I just have one switch and one slider. That's because I've fixed all the other parameter values of the model to default parameters. So if we look at our code window, here are all the parameters of the model. There are many. And then in my setup, the first procedure is called initialize globals. And I'm just setting all of those global parameters to fixed values. I'll just scroll through to show that there's just quite a bit more code for this model than other models. Those of you familiar with other programming languages will notice, though, how much more compact NetLogo model codes are than code that you've written, let's say, in Java or Python or C, and that's because so much is already baked in and running sort of under the hood with NetLogo. Okay. So let's check out our model. So I've started out with one little empire in the corner, and every other cell is an independent chiefdom. And here on this graph, I've plotted the area of the empires coded by the number in which they appear. So the first thing to notice is that after initial growth by the first empire, it's eventually attacked by a small chiefdom and it diminishes as other empires rise. So we get very clear cyclical behavior, empires rising and falling. Let's examine a little bit, though, of how these assumptions make sense. So what if we change the value of h, the power decay? Turns out this is going to have strong effects on political stability. So again, this controls the speed at which, the rate at which power diminishes with distance from the imperial center. So if I decrease this, it actually increases the speed at which power declines. So now power declines fairly rapidly. All right, let's see what happens here. So the first thing we see is that the empires seem to be quite a bit smaller. And that makes some sense because they just can't get as big because power is declining so quickly. So a larger empire just isn't viable. But another thing is also very clear, which is that increasing the speed at which, the rate at which power declines with distance from the center increases cultural stability. So we get the emergence of these moderately sized empires that are pretty stable, with minor border skirmishes kind of oscillating a little bit. And to the extent this model is valid, this indicates that technologies that improve travel and communication over long distances might also lead to larger but less stable societies. And let's go the opposite direction now and see what happens when we allow make sort of travel and communication much more efficient. Now, empires can grow quite large, but as they grow to equilibrium, they become really unstable, and we get very rapid change over time. And sometimes, in versions of this model, the population will just collapse entirely. So now there's no more empires, right? And because the model has no mechanism for new empires to form de novo, we're done. Right? So this further indicates possibly how mobility and communication technologies might contribute to sociopolitical stability, at least under the assumptions of this model. Now let's go back to our default of power decline 2, but just get rid of allowing empires to collapse. So remember in the model, if an empire's asabiya becomes low enough, just on average, the whole empire just instantaneously collapses. And let's just get rid of that assumption. So now an empire can still decline by being captured, right? By being conquered piecemeal by other empires, but it doesn't fully collapse if its asabiya goes lower. And so what happens? Well, we definitely still see cycles, the rising and falling of empires in terms of size. But it's often the same few empires just competing over and over again, just growing and shrinking, growing and shrinking. Very few new empires are emerging. So this indicates that if the other assumptions of the model can be considered valid, the collapse of large empires due to non-military factors is probably essential in understanding historical dynamics. And again, I encourage you to play around with this as much as you like. It's a pretty cool model, and it's got a lot to explore. Okay, the big question, is this theory right? So in his book, Historical Dynamics, Peter Turchin notes a strong similarity between the model output and the actual historical dynamics that we saw already of these empires of East and Central Asia over a 600-year period. So I've reproduced figure 4.4 from this book. So this is a nice demonstration of possibility, right? The assumptions generated the sort of dynamics that are seen empirically. That said, proof of possibility is not necessarily proof of necessity. So the computational social scientist and well-known agent-based modeler Josh Epstein has said in promoting the use of models like this one, quote, "If you didn't grow it, you didn't explain it." I agree that this is a strong argument in favor of modeling. But, however, the inverse doesn't necessarily follow, right? If you did grow it, you have not necessarily explained it. You've only failed to reject a possible explanation. Right? So just because if the model didn't reproduce the historical dynamics, then I think we can clearly say that we didn't explain it. But just because we did produce dynamics using a model that kind of look like the true historical dynamics doesn't mean we've necessarily identified a correct explanation, only a candidate explanation. Actually, in his book, Peter Turchin is pretty clear on this himself, and so it's worth quoting him here. He says, the qualitative similarity between historical polity trajectories and the simulated ones does not, of course, constitute any proof that the theoretical and empirical dynamics are driven by the same mechanisms. Nevertheless, the observation that several features of the model's output match the observed dynamics is, at the very least, an encouragement to test to further theory development and testing. So, obviously, the model is far from a complete theory of historical dynamics or even of just the rise and fall of empires. However, the simple model shows us that the metaethnic frontier idea probably represents a plausible theory and can indeed generate patterns that approximate what we see in history, at least in some places and at some scales. More generally, I'll just say social dynamics are complicated, and models like this give us a foothold to translate our verbal theories into concrete dynamical ideas. It may be that new data will emerge that shows that this model couldn't be right, or it may be that this model is further developed to explain more data. We'll see, but the theory can't be tested until it can be formalized. Okay. Let's talk further directions with these models. So jumping back to our host-pathogen model, this can be used to think about the evolution of contagion. So if one posits a simple mixed population of near infinite size and considers the evolution of pathogen virulence, right, so imagine a giant population with everyone mixing fiercely like a cloud, you must conclude that pathogens should evolve to be as contagious as possible, right? Because that's going to be how they're spread. So having the highest possible transmissibility, the pathogen will spread farther and faster. But as we've seen, the spatial structure that we looked at in the host-pathogen model makes things a little bit more tricky. The conclusion doesn't hold in a spatially structured population of finite size. So there's this nice study by Charles Goodnight et al. Where they allowed traits like transmissibility to mutate and evolve and showed that the consideration of population structure yields the prediction that strains that are overly transmissible will exhaust their local supply of hosts and perish, and the more evolutionarily stable strategy is a moderately transmissible strain. All right, more on historical cycles. So Turchin and colleagues have continued to develop theories of historical dynamics, adding factors including environmental factors like oceans and mountains, technological innovation, conflict among elites, to refine the theory and better fit it with historical data. Models have often also inspired more focused collection of historical and archaeological data, which is also pretty exciting, with an aim to better parameterize dynamic models. growing artificial societies. More generally, there have been a number of attempts to model complex historical dynamics with complex, realistic, agent-based models. One of the first attempts was Epstein and Axtell's 1996 book, Growing Artificial Societies, which includes a careful study of their stylized sugar state model, in which they produce a lot of very interesting social behavior. It's worth checking out. This has been followed by many studies by social scientists and archaeologists to use models to better understand the past. And finally, just more generally, the models we've explored in this unit share principles with a classic sort of model in the physical and biological sciences, those of autocatalytic processes. Many of these models consider substances that are characterized by what's sometimes called local activation and long-range inhibition. That is, the substance is autocatalytic in close range, but faces sometimes indirect inhibition by increased distance from the central zone of influence. So these kinds of forces can generate churning cycles and pattern formation, and such models are widely used to explain processes of chemical and biological pattern formation. They're really cool. Check them out. All right. So that's it for learning about models. I hope you guys enjoyed what we've talked about, and I hope you take the opportunities to play with the code and play with the models and learn more about models and do all sorts of fun stuff. There's one more unit. It's coming up next. It is the coda to this class, in which we'll kind of wrap it up and talk about going further with studying models of social dynamics. Thanks for watching.